Okay, for this week, we are looking into one of the methods used for classification. So in the previous week, before the logistic regression, we study binary and multi-class classification. Okay, so today we will cover one of the methods used for classification tasks. So this is called decision tree. Okay. People like to use decision tree if they want some explanation why some sample are considered positive or negative. Because in decision tree, they can look at the form of the tree. Okay. So what is the decision tree looks like? So if you look at the screen here, decision tree is basically constructed based on the features that we have and the values of that particular feature in your data set. Okay? So the decision tree learner build a model and they will form a tree structure model, something like this. For example, this is your root node where you start, and then you go to the left or to the right, depending on what feature they use in the root node. Okay, what feature they use and what are the values. So depending on the values, you go to the left or to the right. Okay, and you will have a sub-tree again based on some requirement. For instance, this is the basic one. Okay, when we make decision, we look at the, this is when you want to accept a new job or not. So this one, they say, if the salary is at least 50K, then I will further look into the next one, which is if it takes more than 1 hour to reach that working place. If no, then okay, I will consider. Okay, if they offer free coffee, then if yes, then I will accept the job. Okay, so if you look at the structure of this particular tree, all the green one are the leaf, or what we call it, the class label. And in between we have the decision node. So this refer to the features that we use to make the decision and what value will be considered. So in this example, we have a binary value that will be used. You may have multi-way, but this one is 2 ways only. Okay? So for instance, for us to classify class number 2, which is the red rectangle, so what we can do is everything greater than W10 and everything greater than W20 for the X2. So we have 2 variables here. Okay. So whatever fall within this area will be considered as class 2. Okay. So how do we take this particular rule and we construct the tree? So basically we just say, okay, I will take the X1 here. If the value is greater than Y10, I will go here. If less than W10, that is considered as the blue circle. So this is your class label. Okay, and this one is the feature that we use. So in this particular, your feature will be X2 and the value will be this one. So further, we say if this is yes, then we need to further say, okay, if W20 is greater, no, X2 is greater than W20, then we say the class is red rectangle or red square. If no, that means they are circle blue circle. Okay. So that's why that's how we translate the graph into the decision tree. Okay. So the node that we consider here could be univariate. Univariate means a single variable, and then we look at the value for that particular single variable. So it could be numeric. So numeric is like this, values. So if age is less than 30, then you go here. If no, you go here. Or it could be discrete. Okay, so discrete n-way split for n possible values. So for example, we are looking at age less than 30, and then also we are looking at age which is greater than or equal to 30, but not more than 40. And last one is age greater than 40. So we have three ways here. So if the age is greater than, no, less than 30, so we have here B, we go A, B, or C. So we go to B if the age is in between 40 to, no, yeah, 30 to 40. If greater than 40, then you go to C. So this is what we call n-way. So more than two ways. So otherwise we will have binary split. Okay. We could also have multivariate. Multivariate is where you have two variables in the same node to be considered. So for example, in order to split these two classes, we have to draw a line. So the formula would be this. Okay. So in here we have two variables, which are the x1 and x2. So this one use more than one variable, and that they call the multivariate. Okay. So when we talk about the leaf will be considered as your class label. So this is the classification tree. So this one are referring to the number of correct classification, and this one refer to number of incorrect classification. So they said that if you are male and your age greater than or equal to 9.5, so die. So this is more into the Titanic. Okay. So the Titanic case. So at the end here will be your leaf, your class label. Okay, die or survive. This is the classification tree. But if you recall again, last week we covered this regression tree. So in regression tree, basically we are looking at the number. So that is the local fit. No, the average. The average in this particular partition that will reduce the standard deviation value. And this is the how many of the term or how many of the record that fit this area. Okay? So classification tree and regression tree are two different things. In classification tree, the label is the leaf is the label. But for the regression, the leaf will be the average that will reduce the standard deviation. Okay, so if you look at the tree, yeah, like for this tree or any of this example, we will construct the tree, but there must be a stopping condition on how deep or how many level you need to go. Okay, so normally they will choose to stop to split the tree when all the example in that particular node have the same class, or you do not have any remaining feature to be considered to split your data, or the tree has grown to a predefined size limit. For example, you want to go down up to 4 depth. So 4 depth. So after 4 times you consider splitting the data, then you will stop. Okay. So the question here is now, how do we find the best feature to be used to split the data? Because if you see that decision tree, they are formed by splitting the data into 2 partitions and then further breaking them into subset and so on until you find all the members belong to one class only. So the question now is, how do we split them? What criteria that we use in order to split them? Okay. So we look at the purity of the partition. So when we look at the purity of the partition, we're saying that, okay, if the PO is high, meaning that all members belong to one class. Okay, all members belong to one class. Okay, high purity. So meaning that 100%. Okay, but in terms of entropy, entropy will tell you how pure is the partition. So they say if the partition is pure, then the entropy will be 1. Okay, so that is when we have no entropy will be 0. Okay, so when we say entropy is 0, meaning that all the members belong to one class. So if we look at this graph here, this is the positive sample that we have. So when we are here, meaning that all members belong to positive. Over here, all members belong to positive sample in that particular partition. So if we refer to the entropy, this is 0. Okay. So when we are here, so we are saying that all members belongs to negative sample because we do not have positive sample, so must be negative sample. So still the entropy is 0. But if we are here, that means 50% of the sample belong to positive because we have 0.5 here, and 50% belong to negative. So the entropy value here is 1. Okay. So meaning that if we have 50-50, positive and negative, the value of the entropy will be 1. If 100% belong to positive, then entropy will be 0, or 100% belong to negative, entropy will be 0. Okay. So to plot this graph, the formula will be this one. So we look at the probability of having positive sample times log base 2 time log base 2 of probability of having positive class. So we will have positive and negative here. So this is the formula that we use to describe this graph here. Okay. So the entropy will be 0 if this one is 1, when you have the probability of negative is 1, and also the probability of positive is 1. So either this one will give you 0. Okay. Okay, let's take a look at one of the example here. Okay, for example, this one, this is not pure, so the entropy will be not 0 because we have a mix of class level here. So this one is okay because we have pure membership. Okay, so this one will have high purity and this is not, because we have 3 of this. Okay. So what we want to do is we want to have this kind of situation from the beginning, and when we split the data, we want to have this. So one partition will have only a single label membership. We do not want to have this. So that means for this one, we need to split them further. Okay. So the aim is to get high purity or low impurity. Okay. So this one impurity refer to not pure. So what we want to have is high impurity, high purity, or minimum impurity. Okay. So how do we use the formula just now? Okay. For example, we have this partition. How do we measure the entropy value? So the entropy value is used to determine how pure is the partition. Okay. So based on this group, so we have 5A and 3Bs. So these are the probability. So when we plug in the formula that we have for the entropy, so basically this is the formula. They have shortened this one for k number of label. So in this case, we only have 2. So this part is for the A and this part is for the B. So when we solve, we get this value. Okay. So the entropy is somewhere, if we look at the percentage here, so maybe somewhere here or here. Okay, so this is 0.95. Okay. So the most important part is get the probability, plug in the formula, then you can compute. So this is measuring the purity of that one particular partition. So when we look at the decision tree, for example, like this, so this is the data that we use in this example, in which we're trying to model this response. Are we going to play or not? Okay. So based on this value, okay, we pick the outlook. There is a reason why we put outlook here, because in this case, when choosing the outlook, it will give us the highest information gain. We will talk about that one later on. Okay, but when we split the data into 3, because this outlook has three unique values here: sunny, overcast, and rain. So when we split the data using Outlook, we need to look at how many of them belong to yes or no here. So the first one is this: when we split the data into sunny only, so sunny will have 3 no and 2 yes here. Okay, sunny, let me erase. So we have 1, 2, 3, 4, 5. So we have 3 no and 2 yeses. Okay, for the overcast, we have 4 yeses. And then for the rain, we have 3 yes and 2 no. Okay, so before we split the data, this is our partition. And then when we use the Outlook here, then we split into 3 partition. So from 1 partition to 3 partition here. Okay, so we can compute the entropy for each one of these. Okay, for example, the first one is this for the sunny. So for the sunny, we have 3/5 and 2/5. Okay, so this is the entropy for this partition. So this is 0.96. So notice that the entropy value is very high because we have almost 50-50 belong to different class level. Okay, and for this one, we can assume that the entropy is 0 because all of them belong to one class. Okay, so for the overcast, if we plug in the value, so 4/4, because we only have one class, so the value is 0. Okay, and for this one, we have 3 yes and 2 no's. This is similar to what we have here. So basically, we can say, okay, the entropy for this one is 0.96. Okay. Okay. So just now I mentioned about information gain, right? So information gain is used to measure the entropy before you split, which is the entropy for this, and after you split, which is the total entropy that we have for this, and this. So we want to know how much reduction that we can get from before and after. So that is what we call information gain. But before we can go for that one, we have to look at how do we combine the entropy for all these three. Okay, so when we try to combine them, we have to look at the weightage of individual partition that we have. So this is basically the entropy of individual partition. This is the weightage. So we actually sum up all the entropy after multiply them with the weightage of that particular entropy for that particular partition. Okay, so how do we use this formula? Okay, we go back to the previous example here. Let me go forward. They're talking about the information gain here. This is before you split. This is after you split. Okay, so if you go back to the example just now, this is before you split. You need to compute the entropy here, and after you split, you need to combine the entropy for all of these three. So how do you combine? We use this formula. Okay, so this is the weightage for individual partition. This is the entropy. So this is the weightage. And this is the entropy for each partition that we have. So if we have 3 partition, that means we need to sum up all the entropy of that 3 partition. Okay, so this is after you splitting. So if we go back to the information gain here, okay, so this is before you split. No, yeah, this is before you split. Sorry, this is before you split. This is after you split. So by subtracting the entropy after splitting from before splitting, that means we want to know how much reduction of entropy that we can get. Okay. So this is the entropy of each of the partitions. So this is what we have. Okay, so this is the weightage, this is the entropy of each of the partition, and then we sum up. Okay, so how do we apply this one in a real situation? Okay, so we go back to this example just now. So we have this for the first partition, second partition, and the third partition. So we are splitting the data from here. Okay. So the entropy for the first one is 0.96. This is 0. This is 0.96. So to combine all these three, we need to find the weightage. So the weightage for this partition is 5/14 because we have 14 total number of record here. So this is 5/14. This is 4/14. Okay. So since we have all the weightage, this 5/14 times 0.96 plus 5/14 times 0.96 plus 0. So we get this. So this one is basically the entropy for this, and so on. So this is the weightage of the first partition. This is the entropy for the first partition. This is the weightage for the second partition, entropy for the second partition, and this is the weightage for the third partition and the entropy for the third partition. So we compute this one, we get 0.68. So this is the total entropy of all these three partitions that we have. Okay. So what we want to know is what is the information gain. So this is after we split. What is the entropy before we split? So basically we have to go back here. So the initial one is what? The initial one is we have how many nodes? 3, 4, 5. So 5/14 log 2 5/14 plus 9/14 log 2 9/14 okay, so this is before, so this is entropy before, so the total is 0.94. So this is before and this is after. So the information gain will be 0.26. Okay. So the aim is to maximize this information gain that we have by minimizing this. Okay. So this is before you splitting, this is after you splitting. So the aim is to find features and the values that will reduce the entropy. Okay. So for example, like this. Okay, so this one we have the data here. So this is before splitting. So we have 5 no, 5 yes. So 5 no, 5 yes, this is what we get. Okay. And then, okay, given the feature count, okay, feature count, if we use this to split the data, so A, B, C, and D, so for A we have 0, and the weightage is 2/10 because we have 10 values. And for the B, we have 2 no and 1 yes, so that's why we have this. And then the weightage is 3/10. And for the C, we have 3 yes, okay. And then for the D, we have 1 yes, 1 no. So that's why we have this one. So we solve this problem. Okay. So let me show you one more example here. Okay. So not this one. Okay. Okay. Can you see this? Okay. So this is the formula that we get for when we given the count. Okay. We split the data according to the value of the count. Okay. Now let's take total. So if you take total, then the partition of data will be different. So we will have this and this and this and this. So we have 4 partition. Okay. So for this one, the entropy before splitting will be the same. Okay. Now the first one we have 2/2. The second one we have 1/1, and the third one the third one will have 1/2 because we have two sample, but we have no and yes. So this is when the total value is C. And then the last one will be 4 yes and 1 no. Okay. So notice that if you use count, your value will be different here. But the initial entropy will still be the same. So this is the entropy if you use count. This is the entropy when you use total. So the entropy for this one is 0.561. Okay. So the information gain can be obtained by looking at this, because this is supposed to be 1. So we get this 4.39. Okay, so we want to look at this one. So we compare which feature will give you the highest information gain. Then we use that feature to split the data. Okay. Okay, now let's take a look at how do we apply this. So this is bank data. So basically this one is looking at considering 1% applying loan, and then can we approve or not approve the loan. So first we need to look at how do we collect the data, and then prepare the data, and then how do we apply decision tree for training, and then evaluate the model, and then how do we improve the model. Okay. So the data that we get is obtained from the archive ICS.UCI. So they represent the loan from the credit agency in Germany. So this one we are reading the CSV file from my D drive, and this one say maintain all the character as factor. So for example, like this, all of them are considered as factor or label. If this is not included, then that means all of the value will be maintained as a string of character. But in this case, we do not want to have string of character. We want to consider them as label. Okay, like this one, what purpose business car. So this is label. Okay, so we have 17 features, and we have 1,000 sample. Okay, so we can further look into the data that we have. So we are reading into the credit. So our data is in the credit. So this one is just looking at the number of account for the checking balance account. So we have 274 account that has less than 0 Dutch money. So this is Dutch money. And then we have greater than 200 Dutch money. So we have around 63. Between 1 to 200 Dutch money, we have 269. And this is missing value. Okay. We can also look at the balance. How many saving balance that has less than 100 Dutch money? So we have 6 or 3. So this is more into descriptive statistics. We can look at the summary. The summary will give you the mean, the max, and also the average and median of a single feature that you have here. Okay. This is the amount of loan. So the minimum value for the loan is 250. Maximum loan value is 18,000. This is the median. This is the average. Okay. Okay. We also can look at the percentage of those people who default. Default means those people who did not pay the loan. So 70% of all time people did not pay the loan. Okay, and 70% of them always pay on time. Okay? So we want to look at what are the criteria that will make someone not to pay the loan, and decide whether we want to approve the loan or not. Okay, okay. So next step will be, because we want to train the model, so we have to split the data into training dataset and testing dataset. So in this example, we will use 90% of the data, which is 900 sample. Okay. So the statement that we can use is sample here. So we are sampling from 1,000 to 900. So basically, we just produce a random number between 1 to 1000, and we do it 900 times, and we put here. So basically, we are storing the ID of the record that to be used as sample. The set seed is basically used to fix the random number here. Okay, so note that the set seed function is used to ensure that the training and test data can be regenerated with the same sequence of random number. So if you ignore this one, the next time you do sampling, you will get different record. Okay, so if you look at this, the content of this is basically the ID record of 900 sample that we use as a training dataset. Okay, so from there we split them into training and testing. So this one is just creating the data set for the training by including all the record that listed in the train sample. So the train sample is basically listing all the record for the 900 record that we have. So this one will be used for training, and the remaining, okay, because we have minus here, that means we will not include all what we have here. So we will take the remaining as the test. Okay. So if we test the proportion sample that we have for the training and the test, so we still have around the same percentage here. So we have 70% no and 30% yes, similar to the test data set here. Okay, so we have created the training data set and also the test data set. Now we are ready to train our model. Okay, so the next step will be we need to get the model. So we first need to install the package and then upload the package. So this is C 5.0, one of the algorithm called decision tree. They call it C 5.0. Okay. So once we get that one, then we can use this model to produce a model that use the train data set that we have and the class. And the triad is one, means that we only create one tree. Remember that in the decision tree, there are so many trees that we can construct depending on what feature we use in the beginning of the construction. Because we have so many features, right? So we can use feature A or feature B, or we can use feature D to start the construction of the tree. Okay, so once we have trained them, then we use this model here to perform some prediction, use the test data set that we have. And these are the results that we get. So M here refer to the model, P here refer to the result of the prediction. Okay, so what we want to compare is we want to compare this predicted data with the actual data that we have. Okay, so how do we perform this? So basically we are calling the training of the decision tree C 5.0. This is the data that we have. I will include all except the 17 column. The 17 column is the label. So the minus 17 here refer to I will include all my features except the last column, which is in the 17 column, which refer to the label. And then this is the label. So this is basically the train data set. And this is the class. I have this minus 17 because I do not want to include the class feature. Okay, so once I train them, if I look at the tree, so this is how it looks like, the decision tree here. So it says that if your checking balance is greater than 200 Dutch money or unknown, so you are not highly to be default, means you will pay. So this is the number of correctly classified. This is incorrectly classified. Okay. Okay, but if you checking balance is less than 0 or in between this, and also your credit history is perfect and very good, so you are likely to be default. Okay, but this format is difficult to view, but we can reproduce this one using this using the tree that we constructed before in the logistic regression. Okay, so what we can say that if the checking account is unknown or greater than 200 Dutch money, then classify as not likely to default, means you will pay. Otherwise, if the checking account balance is less than 0 Dutch money or between 1 to 200 Dutch money, and your credit history is perfect or very good, then classify as likely to default. Okay. So this one referred to correctly classified, incorrectly classified. Okay. So that's how we interpret this one. Okay. So if you look at this, so once we create the model, so this is your model. This is the summary of the model. So we want to use that model to do the prediction. So here, this is the model. This is the test data set that we have. And then we use the model to predict, and the result is here. Okay. So we can use the cross table here in order to display this table. So this table show you which one are incorrectly classified. So this is the actual label. This is the predicted label. So this is true positive. This is true negative because we have yes and yes. So the error here is this one. This is the error because this is the actual class label, yes, but they are predicted as no. So this is false negative. Okay, for this one, this is the actual data, the actual class, but this is the predicted one. So no, and this is yes. So this is false positive. Because this is considered as yes positive, but they are false. This is considered as no or negative, but they are actually positive, so false negative here. So we want to reduce this error here. So what we can do is we can have many trees. Okay, so how do we improve? We just add this trial here. So the trial here are referring to we will construct 10 trees. So this is considered as random forest tree, random forest. Okay, so instead of using one tree, we can use 10 different model by having 10 trees. Okay, so if we plot the table again, this is what we get. So now this is our error. Since we have 100% data, so the error is 18 per 100. So your accuracy will be 82%. Okay, so compared to the previous one, so the error here is, what is the error? 27. So accuracy will be 73. But this one is using only one tree. In this example, we are using 10. So we have improved the accuracy here. Okay. So in summary, in this session, you need to know how to compute the entropy before and after. So by having this information, then you can compute what is the information gain. So the objective is you want to maximize the information gain by what? By reducing the entropy value after splitting. Okay. So we can use C 5.0 in order to perform the classification, and by adding more trials, you can improve the accuracy of the classification. Okay. Any question? If you okay, if you still there, can you type number 1, 2, 3? Okay. Okay. So I have posted the practical 1 and 2, so you can go ahead do that one. So and also the assignment, I think it's due this week, right? So any question about your assignment? For your assignment number 1, you have to do it manual calculation. No need to do using R. So step by step on how you compute the the cluster assignment for k equal to 2 and k equal to 3, and then the third one is you need to compute the DBI for k equal to 2 and k equal to 3, and then compare. Okay, so everything must be shown in a step-by-step calculation. But for your practical, you need the working file for you to complete, and you will ask to give a snapshot of the output. Okay. Any question? Okay. Let me stop this one.